We are very happy today to have Aya Ismail, who is a course TA and a PhD student in the University of Maryland, to talk about neural architectures, including recurrent neural networks, LSTMs, and transformers. Aya is an expert in this area and also in deep learning interpretability, and we are very happy to have her tell us more about different recurrent neural architectures. Without further ado, Aya, the mic is yours.
Thank you, Sohail. So far what we have looked into is these one-to-one setups where, for example, you have a fixed size input and you produce a fixed size output. And in between that, there is a neural network. So this network, we looked into feed-forward network and convolution network. And this setup was fine for many applications, such as image classification. But it's not very flexible, meaning that we don't always have a fixed size input. So sometimes we have a variable size input. For example, in cases where you have language and you have a sentence which has different length, and then you want to make a prediction. So an example of that is in sentiment analysis, when you look at a review and want to know if this is a positive review or a negative review. Or if you have a sentence and you want to complete it with the next word, so you have a variable size input and you want to make a single output. Also, this is applicable in time series forecasting. So for example, if you have stock, the previous history of a stock, and you want to predict the next, forecast the next stock. So all of these aren't possible with the previous setup. So people started to think about, so what can we do with this variable size input? And that's where recurrent neural networks came in. So what is a recurrent neural network? A recurrent neural network is this architecture where it has a hidden state and it takes an input and produces an output. And this hidden state is basically recurrent in the sense that every single hidden state takes the previous value, the value of the previous hidden state. So if we unroll it, it's going to look like this. So here our current hidden state, h of t, is a function of the previous hidden state, ht minus 1, and our current input, x of t. So if we zoom into a little bit into the architecture, we can find it kind of looks like this, where we have our current input here, we have our old hidden state, and we produce the new hidden state, and in between them there is a tan h. So basically, this f of w is just a weight matrix which we multiply by the previous hidden state, another weight matrix we multiply by the input, and then we pass that through a tan h, and that's our next input. So one reason we're using the tan h here is that we want to add nonlinearity to our neural network. So one thing we want to note is that these weights are shared across cells. So we have the same weights at different cell locations, and these weights keep getting up. The h of t keeps getting up, gets updated by the previous hidden state and the current input. And if we want to make a final prediction, we multiply this h of t with another weight matrix to produce this y of t, which is our output. Okay, so let's take an example, a really simple example. Let's say that we have a language model, and a language model is basically if you have, like, for example, a vocabulary, and you have a couple of words and you want to make the prediction to the next word. So here we have a really simple vocabulary with only 5 words: I am very, not, and hungry. And we have a training sequence, which is I am very. So every single word, we're going to represent it as a word embedding. So since we only have 5 five words, we're going to, so I is going to have like 1 at the beginning and zeros, and then am is going to have 0, 1, and then followed by zeros, and so on and so forth. So if we want to pass this through a recurrent network, how do we do that? So first, we need to have the previous hidden state, but since this is the first time, so we'll just initialize a vector by zeros, and then we're going to multiply this weight matrix with the input, pass it through a tanh, and also we have this previous hidden state, and then we're going to calculate this current hidden state. We're going to repeat that again with am, and then again with vary. And after that, we want to produce the next word, which we are going to multiply the last word, the last hidden state with a weight matrix, and then we have an output. And in this case, for example, a reasonable output would be hungry, not. So I would want the model to tell me I am very hungry. So this is a very simple example of a recurrent network. So let's look at training these networks. But before I go in, does anybody have any questions so far? Okay, moving on.
Aya, can I ask you a question?
Yes.
So why tanh? Why not ReLU?
So we want it to be as like a soft transition. So the first one was the vanilla RNNs were tanh, but after that we kind of started to use sigmoid and tanh. And the one property of tanh is that it gives us this output from -1 to 1. So that's kind of, this is why we use tanh here.
Thank you.
Okay, so so here, somebody asked, was H of Y different from other two matrices? Yes, because it's multiplied by this hidden, it might have different dimensions, and it's multiplied by these hidden layers, not multiplied by, so yeah, it's different from the other two metrics. Has anybody used ReLU? There's a lot of recurrent networks and a lot of cell architectures. I'm not sure if anyone has ReLU inside of them or not. Of course, you can have ReLU like after the recurrent network passed. So if you have, like, for example, your output can pass then through a ReLU and a dense layer, and so on and so forth. But the cell itself, I'm not sure if anyone has a ReLU inside the cell. Okay, so let's look into training this network. So we'll talk a little bit about training recurrent network in the beginning. So what we do is that we make a forward path and calculate a loss. And this loss depends on the problem that we're trying to solve. So for example, we can have, if we're doing a classification, then maybe the loss can be a cross entropy loss. And if we're looking at a regression, such as in forecasting, it can be mean squared error. So once we calculate this loss, we backpropagate through the network and update the weights. And we do that by taking a gradient step, like Suhail described in, I think that was the first lecture. And this is called backpropagation through time because we basically, if you think about the input as different time steps, we move forward into time and then we backpropagate to update the weights. So this is known as backpropagation through time. So let's take a deeper look into how this backpropagation through time happens. So this is a single cell. And we can say that we have this weight matrix here. and we have our inputs, which is the x of t and our previous hidden state. And then we pass it through a tan h. So if we want to look at the gradient path, so if we want to get the gradient of h of t with respect to ht of -1, we only have basically one way. So we're going to follow these red lines to get ht -1. So basically, we're going to, if we calculate it, if we write it out, we're going to get this equation. The equation really itself is not important, but one thing I want you guys to notice that we multiply through this weight matrix. And what happens if we multiply through a weight matrix over and over again if we have a long sequence? So if you have a long sequence, we want to get this gradient of the last one with respect to the first one. We're going to have to keep on going through these, multiplying through these weight matrix at every single time step. So if you don't think about matrices at all, and if we just think about it as a scalar number, if I have a scalar and I have a really long sequence and I multiply by this scalar at every single time step, what's going to happen? Well, we have two options. Either the scalar is going to be small, so we're going to is smaller than 1. So as we keep on multiplying it, it's going to get smaller and smaller, or the scalar number is going to be greater than 1, and when we keep on multiplying it, it's going to get larger and larger. So here, in the case of matrix W, we look into the largest singular value. So if the largest singular value is smaller than 1, then basically what happens is this gradient vanishes. And if the largest singular value is greater than 1, what happens is this gradient explodes. So we end up with this vanishing and exploding gradient, especially when we have this really long sequence. So one thing to note is for the exploding gradient, we can kind of have a way to deal with that. One way is that we can do gradient clipping, which means that in every single time we want to make sure that the gradient we calculate is in a certain limit, and if it's above that limit, we just clip it. And also, we usually have vanishing gradient, not exploding gradient, because the way we initialize our weight matrix are close to 0. So the largest singular value tends to be smaller than 1. So the vanishing gradient problem is more of a problem than the exploding gradient problem. So how do we solve this vanishing gradient problem? So people decided to create this LSTMs, and one thing I want to say is that this LSTM, the first paper came out in 1997, and it's kind of stayed state of the art up till 2017. So it's one of the really powerful neural architectures that stayed for a really long time. Okay, so how is LSTM different from vanilla RNN? So we used to have this really simple gate that just had a single a current input, previous hidden state, and tan h. So now we have this complicated cell with all these different gates. So so we used to have this hidden state, and now we have all of these different gates. We still have a gate that represents hidden state. So this is h of t, which represents the hidden state. But now we have also a cell state. And then we have 4 gates, which is the input gate, forget gate, output gate, and C tilde. So we can think about the first 3 gates as a binary gate because they pass through a sigmoid. So their value is between 0 and 1. So if we think about them as a binary gate, the input gate basically tells us if we want to write or not. The forget gate tells us what do we want to forget from the previous LSTMs, and the output gate tells us what we want to output to the next one. And C tilde of t tells us how much we want to output. So how do they do this exactly? So let's look at this cell state for a second. So the cell state is we have the element-wise multiplication with the forget gate with the previous cell state. So here, basically, if a forget gate is 0 or 1, it tells us how much from the previous cell do we want to carry on forward. And then we have this input gate where it tells us, well, do we want to what do we want to save, or what do we want to keep this for the next time? So is this input going to be written or not? And then we have the C tilde FT. It tells us what exactly we're going to write. So now that we got this cell state, we can then update our hidden state, which is basically we multiply that with the output state, which tells us exactly like for each element, what do we want to reveal to the outside world? So if we think about the LSTM cell as a like its own world, and it just has an input and output, and we can't see anything inside of it. We only see the HFT and the CFTs. So how much of information of what we have inside do we want to reveal to the outside world? And this is the basic structure of the LSTMs. So before I move on, does anybody have any questions? Okay. So let's take a closer look into the LSTM cells. So we can think about it as we have an input, previous hidden state. We multiply by a weight matrix like we had previously. And then we have these 4 gates. And then on the top, there is this cell state that keeps on updating every LSTM cell. And as you guys remember, we said that LSTMs were created to solve this vanishing and exploding gradient problem. So what happens when we backpropagate through an LSTM, and how is that different from backpropagating through an RNN? So one way to backpropagate through an LSTM is going through this path, the red line here, from the cell state, the current cell state, to the previous cell state. And basically here we have just 2 operations. The first one is addition, so there's no problem there. And the second one is multiplication, but it's element-wise multiplication with the forget gate. So if we go through this path, there is no multiplication with a weight matrix whatsoever. The other path is going through this through the gates and going through the weight matrix, and then getting the HT minus 1. So you can think about this upper pass as a highway for the gradient to flow as we go on from one cell to another. So let's calculate the derivative of HFT with respect to HFT minus 1, like we did previously. So okay, I have just one question, so I'm going to go back a bit. So these gates, so we have I represents the input gate, O represents the output gate, and F represents the forget gate. And you can think about them as a binary embedding with values 0 and 1, because they are sigmoid, and then they just turn off and on, which tells us, do we want this information? Are we going to keep it? Are we going to forget it? Which input are we going to have, and which are we going to output? So the other one, will it be the same as calculating through the original path? So no. So let's take a look about how we're going to calculate the gradient. So here, like we said, now we have 2 paths. We have this top path, and then we have this kind of bottom path. So if we write the derivative, we get this huge equation. And remembering what we said previously, when we have these weight matrices and we multiply them over and over again, assuming that we initialize them to be small values, they're going to eventually vanish, right? So we end up with something that looks like this, which is basically the forget gate, which is an element-wise multiplication, times the output and the cell state. And so there's that, now that we have this nice gradient property where we can always move from any like a different path, there's always a different path from the output to the input through the gradient here. So we don't have this vanishing and exploding gradient problem anymore. So is that clear? So do LSTM outperform RNNs in small sequence? Yes, they do. So even in a really small sequence, there is this gradient vanishing. So for example, even if you have a 4 sequence, the gradient is not going to be the same in the first one like the other one. So there's always this gradient problem. But also the cells that they added helps the performance. And also usually the sequence, if you think about language, the sequence are pretty large. So you usually have this problem. So that's why they kind of came up with LSTM. But yes, LSTM do outperform RNN in most applications, I think in all of them. Why is it an approximate evaluation? Because it's basically we keep on multiplying by this entire equation over and over again. And if we say that everything that's multiplied by W, which is the weight matrix, is going to vanish, then this is kind of what's left, because they don't go to exactly 0, or we don't know when they're going to go to 0. So that's why it's an approximation. For long sequence, will the others become 0? Yes, basically the others are just going to vanish, and this is what we're going to have. But then we have this gradient pass, so we can update the weights and calculate the loss, and we don't have a problem anymore. So any other questions? Okay, so by doing that, by having this kind of gradient highway, we have a gradient flow from different hidden states to the input where we can update the weights. And people kind of started to think about these gates. Are they kind of magical? Why are there 4 gates? Why not have 3 gates? And there has been a couple of other architectures, recurrent architectures, but LSTM still remains one of the most popular ones. And the combination of the gates and kind of preserve this property of the gradient flow, so we kind of need them. So that's why it has been successful for 20 years. Okay, let's take a look at actually using an LSTM. So we have a sentence, I am, and we want to complete it. So we're going to pass the first embedding to the first LSTM cell, and then the second one, and then we're going to have a produce and output. Let's say I'm going to say our network is going to say I am short. And it's a perfectly fine sentence, I am short, we don't have any problem. Okay, let's say that after my prediction, there's the rest of the sentence. So I am dot, and then hungry, I could eat a cow. LSTM at a certain point where you make your prediction only saw I am. So if it says I am short, which is completely reasonable, but when you complete the sentence, I am short, hungry, I could eat a cow, it makes no sense. So why is this happening? It's because LSTM preserves information from the past, and at a state, we only see the current inputs and the past inputs. We don't see the future. So how do we solve this? People started thinking about this bidirectional RNN. So by bidirectional RNN, it can be any type of recurrent cells. So what's a bidirectional RNN? It's basically just 2 RNNs stacked on top of each other. The first one is what we had previously, where we give an LSTM the inputs, and we produce a hidden state. And then we give this input in sequential order. So we give it the first input, second input, and third input, and so on. And then we have another LSTM, which takes the input in reversed order. So it takes the last one and the one before it and the one before it. And then it produces also a hidden state. So then we concatenate these different hidden states, and these are the hidden states we actually use. So now at every single time, we kind of saw the past and we also saw the future from the other one. And now when we have I am dot hungry, I could eat a cow, it kind of knows that it can't use short, it should have I am very. So this is kind of why people started thinking about this bidirectional LSTM, which are basically just two LSTMs stacked on top of each other and take an input in reverse direction. So any questions so far? But still we'll have the problem in online input setting. Yes, so we assume that we have the entire example here. So we have this entire sentence and we want to make an output. And also, if you think about even in human, if you're in online input and you give me just I am, I can tell you anything and it's going to be correct. So it just assumes that we have this entire sentence, but the previous structure, we weren't able to use hungry, I could eat a cow, but now we're able to use that information through this bidirectional architecture. Any other questions? Okay. So far we talked about this one-to-one and this many-to-one, where we have a variable input and produce a single output. We have another setting where we have a variable input and we have multiple outputs. And that's, for example, is in machine translation, where you have a English sentence and you want to produce a Chinese sentence or a French sentence. So the current architecture, we can't really deal with that right now. So how people started to think about, well, we can have this encoder-decoder recurrent neural network, and it's called seek-to-seek because we have a sequence and we have the input sequence and we produce another output sequence. So the goal is that you have a input sequence, which is the source, and you want to produce an output sequence, which is the target, and both of them may have arbitrary length. So we have an encoder, which can be a LSTM, for example, and we give it the input sequentially. And then after that, we produce this context vector. And then this context vector is inputted into a decoder, which is also an LSTM, and it produces the output also sequentially. So this it doesn't really have to be an LSTM. We can use any recurrent cell. It can be an RNN, but it won't perform well probably. It can be a GRU, which is another type of recurrent cell. So one thing to note here is that the first input takes this context vector, which is the output of this last word. And this is kind of a problem because when we have a really long word, a really long sentence, we kind of tend to forget what's in the front and just focus on the end. So this kind of started to be a problem when we want to translate paragraphs, for example, or even if we just want to translate a short sentence, but the important words needed for translation are in the beginning. So how do we solve this? People started to think about attention. So before I go into that, I'll just read the questions. But we still have this problem in online setting. Could we have used an LSTM, but output at time t some t minus k output? I'm not sure what you mean about that. So if you could clarify or unmute yourself. So we want a delayed output. Yes, but the cells, even if we have a delayed output, the cell structure didn't see it. So if we go back to this LSTM, even if we have inputs here and we want to look at this word, which is the output, the second word, it won't have seen the future.
Yeah,
So
yeah. For that, what I was saying is, why not like have a few words in the future as well and predict a little later? And since we are working with online systems, then uh, like 100 millisecond won't be a problem. Like if
yes,
we
but
take,
then it's not going to be online if you're going to have the next word.
no, I mean huh, it's not exactly online, but it has some future context, but it works in real time.
Okay, so basically what it's going to do, so which word, so let's think about it a little bit. If you have these cells, if we have like 3 and we want to make the prediction of the second word, right? You're going to look at this hidden state, right? Is the second one to make to produce and use that to make your output. So if you already process the third word and you process the fourth word, you're still going to look at this word, the second word, right?
Yeah. I am inputting the second word's output based on the third and fourth inputs as well, so that I have the future context as well.
So basically you're kind of looking into the future, which is basically what bidirectional RNN is doing, except that you're just making it smaller.
Yes.
So yeah, so that's how kind of they came up with this idea, except that you don't really have to do it online, you can do it entirely offline. So in your context, we have an LSTM, a bidirectional LSTM, which has a really short memory in the sense that we only look 2 words ahead or keywords ahead.
Mm-hmm. Yeah, that's all. Thank you.
Okay. I have another question. So can we say why people started to think about attention? So people started to think about attention because we have this we have this context vector, which is the input to our decoder. And first of all, it has 2 problems. The first problem is that it's outputted from the encoder after it's done. So it tends to focus on the last couple of words, and it forgets what's in the beginning. Remember that we have this forget gate that tells us when to forget. So at this point, there's a lot of stuff from the beginning that we already forgot. And actually, the words in the beginning are might be really important to make our translation. So we don't really want to forget them, and we kind of want to focus on different words from different time steps. So this is kind of why the idea of attention came up. Okay, so the goal of the attention is to help memorize long sequence in neural translation. This is the initial idea for attention. So basically, if we have this encoder, instead of looking at the context vector from Apple, so I want to look at the entire sequence. But I can't just look at this sequence. How am I going to give that to the decoder? So basically what I'm going to do is that I'm going to multiply every single word with a weight. So this weight represents the importance of that word in the translation. So we have this context vector from every single word. We multiply that by alpha, which is here our attention weight, and we make the first translation. Then we do the same thing with new words and so on and so forth, and we keep on moving forward. So at every single decoder cell, instead of just having our previous input, we have this input and the context vector multiplied by the attention. Okay, so let's look into it a little bit more closer. So here we have a source and target. which is basically our input and our translation. Here, this is a bidirectional LSTM. Our encoder, so bidirectional LSTM, and then we have a decoder, which is just a regular LSTM. And then now our input to the decoder is, instead of having just the previous input and the previous hidden state and the current input, we also have this C of I. And C of I is basically the context vector that we mentioned. So how do we get this context vector? Well, we have this alignment suite, which tells us which word is important to every other word. And then we multiply the alignment suite with the hidden state to get this context vector. So we end up having something that looks like this, which is called the attention matrix. So for example, this is an English sentence that is translated into French. And during the translation, we can see that 1992 is the most important value for this translation was actually 1992. And August was also aligned with August in French. So these were kind of the most important things. So you have this weight alignment or this attention matrix where it tells you the importance of every word with respect to every other word. And you add that information to the decoder and you end up not forgetting and being able to use all the sentence to make the translation. So this is basically the idea of attention. So any questions about encoder-decoder attention? Okay. So what if we're not using, we're not doing machine translation? What if we're just doing classification? Can we use these attention mechanisms? Can we, or does this attention have to be between an encoder and decoder? So given that question, people started thinking about self-attention. And what self-attention means is that instead of looking at the current, instead of looking at the encoder, we're going to look at basically our values. So let's take an example to understand it a bit. So here we have our input, and then it's passed through a bidirectional LSTM. And we're going to put the hidden states. We're going to concatenate together and have this matrix capital H, which is basically the hidden states from this bidirectional LSTM. We're going to multiply this hidden state with attention weights using this operation here. So what does this operation do? Well, basically it takes these hidden states, multiply it by this weight matrix, WS of 1, and then passes through a tan H, multiply it through another weight matrix, and passes it through a softmax. And it uses a softmax to make sure that all of these weights are between 0 and 1. So now, given a hidden matrix H of H transpose, we have this attention weight, which tells us the weights for every single value, every single hidden state. So we have a weight for every single hidden states that sum up to 1. And then we take these hidden states, we multiply it with their weights, and then we have this new matrix M. We flatten this matrix and we pass it through the dense layer and the softmax, and we continue with our classification. And we call this self-attention because basically we're attending to ourselves and there is no encoder and decoder. And when people started using self-attention, it improved the performance of recurrent networks dramatically. So that's kind of what self-attention means. There's different types of self-attention. This is called multi-layer perceptron self-attention, because if you can look at this weight matrix times H, tan H, and weight matrix, you can think about it as a small feed-forward network. So moving on, before I go on, does anybody have any questions about self-attention and or attention in general, anything we talked about so far? Okay, so we talked about this one-to-one. We have a question. Why do we still need recurrent structure if we have attention? So why do we still need recurrent structure if we have attention? Well, you're going to have to wait for that in 1 second, and we'll look into that. So we had this one-to-one relationship. We had this many-to-one relationship, many-to-many. Are there other possibilities? Well, we can have like one-to-many, where we have an image and we want to have a caption. So usually you would deal with this is that you pass this image through a convolution network and you have this feature representation of the image, and then you pass it through an RNN and predict the sequence. We also can have something that's like many-to-many, where you have a video and every single frame you want to produce an output, and you would do something similar. But given that what we have so far from the recurrent neural networks and convolution neural networks, we can basically perform all of these tasks where it's one-to-one, one-to-many, many-to-one, and so on and so forth. Okay, so the question that was just asked, do we need RNNs at all? And people started thinking about, well, we have this attention, which is cross attention from the encoder to the decoder, and we have the self-attention. Why do we need RNNs? So they came up with this structure called the transformer that did not use RNNs, and basically it's just self-attention. So the transformer was first designed for machine translation. Like we have an input, we pass it through the transformer, and we want to make an output. And like we said, these are variable length input and variable length output. Like we had previously, we have an encoder that encodes the input and the decoder that produces output. So far, it's basically the same structure. Here's when things started to get interesting. So they said, well, we're not going to have a single encoder, and we're not going to have a single decoder. We're going to have a sequence of encoders, and then the last one we're going to use as an input to a sequence of decoders. Okay, so let's look at the structure of the transformer a little bit closer. So this is what a transformer looked like in the first paper that came out in 2017 with the name "Attention is All You Need." So you have this input, and then you have an input embedding. You pass it through a positional encoding, and then you have an encoder, which is multiplied n times. You take the last one and you pass it through a decoder, which is also, you have n decoders. Okay, let's take this structure and break it down a little bit. So let's say that we have this example thinking machines, and we have only one encoder. So we take that, pass it through a positional encoding, then we do self-attention and add a normalized feed forward, and then add a normalize. So what does this mean? Okay, let's start with the positional encoding. So previously, let's say that I have a sentence that has the same word twice. How did a recurrent neural network handle this? It knew which word this is, the position of the word, because it takes the input sequentially. So it knows that this is the second word, not the first word. So for example, if we had, I went to a room and then left and went into another room, so these two rooms are not the same. And the recurrent network knows this because, well, it knows when this word was inputted. But in this, if you think about it as the word embedding, it's the room and room have the same word embeddings. So how do we put this, how do we know which word this is? So they added something called a positional encoder. So what's a positional encoder? It's just basically a sine and a cosine waves, which tells me, which I add to the embedding to tell me which position this word came into. So I have my input, I add this positional encoding, and then I get this embedding, which is the embedding with the time. Okay, before I move into self-attention here, does anybody have any questions? Okay, so self-attention here is a bit more complicated than what we had. What other functions are valid for positional encoding? So there's a lot of positional encoding that came out after this. This was the one introduced into the original paper, but you can actually, most successful encoders are actually learned. So you learn this positional encoding instead of having it as a like predefined function. So that was most successful. Okay, let's get into the self-attention. So let's think about a database. If you have a query and you have different keys and you want to query that database. So what would you do? You would basically take this query and look at the keys and check out the one that matches the query the most. So this is kind of the idea that they're going to apply here. We have this input X, and then we're going to multiply it by 3 different weight metrics. One is called WQ for query, WK for key, and WV for value. And now we have these new new inputs Q, K, and value, which represents the input in the query, key, and value. So how do we know which query matches which key? So here they just multiply it. So for every single query and key, we're going to have a score. So how are we going to calculate that score? We're going to multiply the query times the key, and then we're going to normalize it, pass it through a softmax, and now we have a probability for every word with every other word. Okay, and then we're going to multiply that by our value, and then we're going to have our output. So it kind of looks like this. We just have this query multiplied by the key over root D, which is the dimension of the embedding. This is just to make sure that the values are nice, and then they pass it through a softmax to make sure that they sum up to just all of the scores sum up to 1, and after that they multiply it through the value, and then we end up with these new matrix set. So this is called self-attention here, but this is single head self-attention. So what does that mean is that we only have one key, one query, one value, and we get the attention with every word with respect to another. Here's when things get a little bit complicated. So instead of having one head, we're going to have n heads. So n here in their first architecture was 8. So basically, instead of having one query key and value, we're going to have n query key and values. And we're going to get these by having different matrix that represents different weight matrix that represents different heads. And we're going to repeat this operation that we did before, and every single head is going to produce this new matrix set. So now instead of having one Z, we have n Zs, and here n was 8 because we have 8 heads. So given this 8 heads, we then multiply them through this huge weight matrix, WO, and then we end up with a single Z. And that's basically this single block, which is self-attention. So before I move on, do you guys have any questions? Why multiply the heads? So we didn't multiply the heads, we concatenated them and multiplied by a weight matrix to get like this reasonable size output. I meant, oh, so why do we have n heads? That's a really good question. So basically, what do this query value represent? They represent the representation of x in a certain dimension. So basically, when you have these different heads, you have different representation that represents inputs differently. So instead of having only one feature representation for this input, you have multiple feature representation. And this improves the performance of this transformer dramatically. Can we take the average over the head outputs instead of concatenating them? Yes, we can, but concatenating them and multiplying them produces better results. I'm not sure if anybody has averaging. Okay, so we're done with the first cell, which is multi-head self-attention. And if we wanted to look at this entire figure, so we have this word, and then we get this word embedding. We pass it through positional encoding. And then we have these different weights for different heads. We multiply the input with it, and we get these different queries, keys, and values. For every single query, key, and value, we calculate its Z, and then we concatenate these Z together, multiply by a weight matrix, and then we have the output. And this is just this first multi-head self-attention. This is what it looks like, basically. And again, we have multiple heads because they represent features in for different feature representation. And now the output has the same dimension as the Z we want because we multiplied by this huge weight matrix. Okay, so let's zoom in a little bit. So these inputs, positional encoding, and then we have the inputs with the positional encoding. We do multi-head self-attention, and we get an output. So here we have this skip connection where we add the output, Z, with the input, and then we do layer normalization. And then we have this new output, which we pass through a feed-forward network. And also we have this skip connection where we also add it and do another layer normalization. And then this is the output of the encoder. So we start stacking encoders, and in the initial paper they had 6 encoders. So the output of the the first encoder is the output of this last add and normalize layer. And then we're going to do self-attention on that and repeat that operation over and over 6 times. So 6 is not the magic number, and also 8 for the heads is not the magic number. There has been architectures with more than 6, and also you can have different number of heads. Okay, so this is for the encoder. What happens in the decoder? So the decoder looks exactly like the encoder, except that we have this encoder-decoder attention in addition to the self-attention. So what do you guys think this encoder-decoder attention does? And how is it related to what we talked about previously? Any suggestions? Yes, so it basically decides which output we want to focus on from the input. So somebody else said remember the context at each time step of the output sequence. Yes, so basically this here this attention, instead of having self-attention where we have a weight for every word with every other word in that input, we have a weight with every word with inputs from the encoder. And we also have our own self-attention that we previously had. So the only difference between the encoder and decoder is this encoder-decoder attention. And we take this attention from the last encoder and we pass it on to every single decoder. Okay, so that's the transformer architecture. And it basically, when this came out, it revolutionized NLP and anything basically that uses sequence. And it also really fast to train because you can parallelize it. So it's really fast on a GPU. And people started using this transformer architectures to create other architectures like BERT, GPT, and Elmo, and all of them are based on this transformer with different types of layer normalization, with different number of encoders, different decoders trained on different tasks. And also we started to have like these pre-trained networks, like for example GPT and BERT, which you can just use them and use their embedding and fine-tune them on your task, and it outperforms all what we usually had. So up till 2017, everybody was using recurrent networks or LSTMs, and then Transformer came, and basically now that's what everybody started using, and it improved the state of the art dramatically. So so this is all for transformers. If anybody has any questions, I would, yeah, this is a good time to ask. You can unmute yourself or write in the chat. Could you repeat why we need a decoder? So we need a decoder because we want to produce a sequence. So if we're, for example, if we're doing a classification problem, we would just throw away this decoder, and we would have, after the last encoder, we would have like a dense layer and a softmax, and we do classification. But like we talked about in the seek-to-seek, where you want to have an input sequence and you want to produce an output sequence, you need to have a decoder to be able to do that. Other questions? Seek to seek into new domains. So what do you mean by new domains?
So to clarify,
yes?
sorry, yeah. So to clarify, I guess like if we think of machine translation as this abstract task, and we have specific instances of going between like English and French, have anybody tried to fully abstract that, or is there a way to make it so that whatever model we train for one of these machine translation tasks only requires like a little bit of tuning in order to make it work for the others, or is the domain too important?
So and stuff like, for example, BERT, they kind of trained, I can't remember what the task they were training on, but it's basically they trained their network on a really big data. I think it was Wikipedia and book corpus, and after that they were able to have this really strong embedding that people would just fine-tune, and sometimes they would just like freeze some of the layers and just fine-tune the other layers and use it in another translation. So you can have a network that is trained on English to French, and then if you train it really well, it kind of starts to learn English really well. And then if you want to remove French and put another language, you can have like change the decoder. I don't know how well it's going to work though. You can't expect structures. It's going to depend a lot on the structure of the language. Like for example, if you're thinking about English and French, maybe they have the same word alignment, but if you go to think about like Chinese, it's going to be very different. So yes, we have these networks that are pre-trained and we can use them and fine-tune them, but it depends on the transfer, basically depends on how well these languages are related to each other and other factors.
Thank you. Yeah, that makes sense. I guess one follow-up question is there any way for us to know whether we're actually learning these sort of like high-level abstract like semantic meanings at different levels of our encoder? So we have these 6 encoders. Is there a way for us to peer into the the transformer and say, at this point, we're picking up meaning that, kind of transcends the language.
Yes, so that's a really good question. And there is like a ton of papers trying to just think about what are we actually learning. So what are the different encoders learning? And what are the different head learning? And why do we need all these encoders and different heads? So basically, there's no right answer and wrong answer. It's basically, so usually the encoders at the beginning are learning stuff that has to do with the word structure, but the encoders at the end basically kind of learn the relationship between the entire sentence, because they have passed through different encoders and they kind of learn the high level language. So that's and different heads looks at different properties of the words. So that's why they use different heads. Exactly what happens is kind of a black box for us right now, but the idea of multiple encoders is basically to learn different properties as we go on in the sentence. So high level upper encoders should have learned stuff about the sentence structure, and lower ones should have learned more about the words.
Hi, how did we have like a variable sequence length in the decoder? Like the number of words that we have in the encoder, that is the number of encoder outputs Z we had, right?
Yes. So yeah, so that's the input to the encoder. And then we have the output. The output of the last encoder is the input to this multi-head attention.
Yeah.
And then we can keep on producing words in the same sense that we would do in a seek-to-seek. Like here we would have this output, we would produce words as a sequence with this positional embedding. So exactly the same way we would do it in an encoder and decoder, we would have the same architecture here.
Okay. So yeah, like I didn't understand this. Like if we have say 10 words, so we get 10 Z encodings. How are we inserting it into the decoder so we get say 12 output words?
Okay, so basically what you're going to get is you're going to keep on producing words, right? So what you're going to do is that you're going to produce a single word, can think about it like that, and you're going to, for that word, you're going to get the attention of that word with all of the encoders, right? And you're going to produce this word, and then now we have one word, and then you get that, you produce another word, and so on and so forth. So
oh yeah,
yes.
yeah, I see the output shifted part in the decoder. Thanks.
Oh yes.
Yeah, I didn't get to see that before. Thanks.
Other questions? Okay, so this is basically for transformers, and yeah, and like I said, people started using these pre-trained transformers for different tasks, and they do really well. So this is all I have today for neural architectures. So Sohail, you can take from here.
Thank you, Aya. Let's all thank Aya for this great presentation.